All right, guys. So today we're going to focus in on wrapping our minds around what's called the greenhouse effect, and what role the greenhouse effect, or what we might term the enhanced greenhouse effect, it could be playing in the surface temperature trend we've been discussing for the past few days. All right. So when we talk about the greenhouse effect in our atmosphere, we are talking about the various gases, right, in the atmosphere that absorb and re-radiate infrared energy specifically. Now, the reason infrared is important there will come up here in just a minute. All right. So we're going to draw some diagrams, and I'll apologize ahead of time for the randomness that this might appear to have, but I'll do some explaining as we go. So here's our Earth system. This is not to scale, obviously. Earth. Right. I'm going to draw a blue dashed line to represent our atmosphere. All right. And then we'll have our sun. Happy little sun. Like a Bob Ross painting, right? So now, in our class, we've already discussed, right, the fact that the sun sends an energy at us, right? And I'm just going to draw that as a squiggly line to represent that it does come in electromagnetic waves of various wavelengths, all kinds of wavelengths from the sun, actually, all right? So, and the amount of energy that the sun sends or gives off or is received by the Earth, the total amount doesn't change very much. There's some little cycles, and we've already talked about those in class, but by and large, that's a constant amount, okay? Now, what does change over time, and this helps to explain climate change in the past, ice age, interglacial periods, etc., right? What does change is what happens to that solar energy as it enters the Earth's system. How much gets reflected? How much gets absorbed by the surface, right? How much is reflected by the atmosphere? How much is absorbed by the atmosphere? And that change that occurs over time and how much gets reflected and how much gets absorbed can impact, right, the equilibrium surface temperature of the Earth, right? And that's what helps us understand these shifts towards ice ages and shifts towards interglacials, all these feedback loops that we've talked about that come into play. All right, so what we're going to look at today in this set of notes is what role does the greenhouse effect play in that interaction between solar energy and the Earth system. Okay, so first of all, we've done that energy budget graph before, right? But we have to remember that some of that energy is immediately reflected. All right? So we have some immediate reflection by particles in the atmosphere and so on, okay? And that would be referred to as the albedo of our atmosphere, okay? And if you recall, there's aerosol particles, particulates, and so on that just reflect solar energy back out to space before it has much of a chance to heat up our lower atmosphere and our surface. All right, volcanic eruptions, when they occur, right, can temporarily increase that albedo. And we can see after a large volcanic eruption, such as Mount Pinatubo in 1991, a little dip in surface temperatures, which makes perfect sense because there was an excessive amount of particles from the volcano up in the atmosphere that reflected sunlight back. Little dip in temperatures, okay, temporarily. All right, but so we got some that's immediately reflected, and we have some. I'm going to draw like kind of horizontal arrows off this one. It's immediately absorbed. That says immediate absorption, by the way. This is my really sloppy writing. So we get some sunlight reflected, some absorbed immediately by the atmosphere. Now, we also have to remember that when sunlight hits the surface of the Earth, the albedo of the surface is going to impact how much gets absorbed, how much gets reflected. So I'm going to draw another squiggly line here. right? So again, that's not extra energy coming from the sun. I just wanted another line to work from, right? So we're gonna have some immediately reflected, right? And we're gonna have some, and I'm gonna draw it this way. So we're gonna call this, so we have, let's say this is the northern latitudes, right? Sunlight comes in, hits a giant ice sheet. Much of that energy just gets reflected right back out and doesn't cause as much heat, right? That's the importance of albedo. Now, some of the sunlight that hits the surface gets absorbed all right? And then I'm gonna draw long wave radiation here, right? This is infra, I-N-F-R-A, red radiation. Okay, so basically, with the amount of sunlight that gets absorbed by a surface, right? The ground, right, or blacktop or whatever, receives sunlight, absorbs some of it, right? As that warms up, it's going to then radiate some of that energy back into the atmosphere, right? But the temperatures or the amount of energy that's given off is in that infrared spectrum, right? So one of the things I want you guys to understand is that yes, there's some immediate absorption by the atmosphere of sunlight coming in, but much of the warming of our atmosphere, not all of it, but much of it actually comes from the ground surface, right? And the surface begins to warm the air above it, right? It's the radiation of absorbed energy from the surface works its way into the atmosphere. Now, nighttime, right? So Earth rotates enough, sunlight is no longer hitting our surface. What slowly happens through our nighttime is we have no more incoming radiation, we just have outgoing radiation, and that's why it cools off at night. That radiation works its way up through the atmosphere and escapes to space. Okay, so we get those changes between daytime warming, right? Sunsets, we get radiational cooling at night. Now, how much cooling we get at night is dependent on lots of atmospheric factors, right? How much humidity is in the atmosphere. The more water vapor we have in the atmosphere, right? The longer or the more energy kind of gets stored in the atmosphere, and therefore the cools off a little more slowly. But there's cloudy at night, right? Interestingly enough, if I put some clouds into this system, right? So let's say I have a cloud right here, right? In the daytime, clouds are going to reflect energy back out. So that's why generally cloudy days are cooler than our sunny days, okay? But the same thing actually happens at night from the other side of clouds. If we have a cloudy night, right? The infrared energy that is beginning to radiate out actually gets absorbed by a cloud and then sent back to the surface again, okay? Part of the reason our cloudy nights don't cool off as rapidly as our clear nights, because there's clouds there to absorb some of that outgoing radiation, right? And re-radiate some of it back down to the surface. Okay, so I'm gonna erase some of these arrows, assuming you guys already have some of that written down. But again, summary, bit more or less constant amount of energy from the sun. Some of it gets reflected immediately by the atmosphere. Some of it gets reflected more or less by the surface, where we have a high albedo. Some of that energy gets absorbed by the atmosphere immediately, warms the atmosphere up. Much of the energy gets absorbed by the surface of the Earth, right? And then that energy absorbed by the surface heats the air in the atmosphere above it during the daytime, okay? At nighttime, when there's no more sunlight hitting the surface, we get slow radiational cooling. How slow or how fast that occurs depends on lots of factors, such as, is it cloudy or clear? Is there a lot of high humidity, low humidity, that kind of thing. All right, now let's look at the role of our greenhouse gases now. And this is why I want to erase some of this messiness of my drawing. But I'm just going to redraw my entire atmosphere here. All right. Okay, and I'm gonna do my radiation from the sun hitting the surface, long wave infrared radiation escaping. Okay, now in the atmosphere, right, there are several different types of gases that we call greenhouse gases. And the reason we call them greenhouse gases is that they have a property, right, in their molecular shape and bond length perhaps, right, that allows them to absorb outgoing infrared radiation and re-radiate it, right? So various gases in the atmosphere that absorb and re-radiate infrared energy. So the primary gases that we refer to in terms of greenhouse gases are, well, water vapor is one of them, right? That's why I talked about humidity, high humidity. When there's lots of water in the atmosphere, it tends to hold on, right? Or absorb more of that solar energy, outgoing infrared energy, right? Carbon dioxide is an important one. Methane, nitrous oxides, and a class of compounds called CFCs, chlorofluorocarbons, right? And those exist in various quantities in our atmosphere, all right? And each of those gases has various abilities to absorb this outgoing infrared radiation and re-radiate it. And so let's take our most abundant of these gases is carbon dioxide, and it's the one that gets talked about most in terms of greenhouse effect and climate change, right? But to kind of illustrate this, so we have some outgoing infrared radiation, right? Can get absorbed by carbon dioxide and then re-radiated by that carbon dioxide, right? Now it does get re-radiated in all directions. That's how radiation works. But one of those directions is back down to the surface, okay? Same thing with methane. Outgoing infrared radiation, some of that gets absorbed by methane molecules and re-radiated, okay? CFCs, nitrous oxides, water vapor, all of those different molecules have that same property, right? To various degrees. Now, what that means, okay, again, how much of this solar energy gets reflected and how much gets absorbed, right, over time, impacts the average surface temperature of our Earth, okay? And so the net effect of having greenhouse gases in our atmosphere is that they prevent much of the radiational cooling at night that would occur in the absence of those gases, all right? And so overall, they help keep our surface temperatures at a functional level, right? So if we didn't have any greenhouse gases in our atmosphere, we would likely be a large ice planet, right? Most of our water would in fact be frozen. So we have so much radiational cooling at night, the average surface temperature would be much cooler, okay? So the greenhouse effect is a naturally occurring phenomenon, all right? And it occurs because we do have certain gases in our atmosphere that don't allow infrared radiation to escape our lower atmosphere as quickly at night, or even during the day, mind you, as it would otherwise. And so therefore, we're able to retain some of that energy from the sun in the lower atmosphere for a longer period of time. And that keeps things a much more mild temperature, much more livable for us and other organisms. All right, now, what we want to differentiate here though now is what's referred to as the enhanced greenhouse effect. And all that enhanced greenhouse effect is the greenhouse effect, right? In which case we have an increased quantity of our greenhouse gases, right? So if we have a low abundance of these greenhouse gases in our atmosphere, less of that outgoing infrared radiation is able to be absorbed and re-radiated back to the surface, and that would result in more radiational cooling and a decrease in the average surface temperature of the Earth because it would be able to radiate out more quickly. All right, now If we increase the abundance of these gases, the side of that equation would happen, in which case less infrared radiation would escape, or would escape more slowly over time, all right? And that would result in kind of bringing our net temperatures up. So the way a greenhouse, when we say greenhouse, in terms of like where we put our plants to get them started, you know, when it's maybe still too cold outside, right? The way a greenhouse works is much the same way, not exactly, but much the same way. Greenhouse, I'll actually draw it green, right? Is typically made of glass or plastic, but it's clear. And what it does, right, is it allows certain wavelengths of infrared radiation into that greenhouse, okay? And so shortwave radiation, so types of radiation that are not infrared, for example, are able to penetrate that glass, and that warms up the surfaces inside that greenhouse, all right? Now, the surfaces then try to radiate that energy back out, but just like what gets radiated out by the surface of the Earth, the outgoing radiation that would occur there, I'm gonna draw it green or red or blue here, there we go. The outgoing radiation, right, that's infrared actually is not able to penetrate things like glass very well, all right? And so what happens is we have lots of energy going in and less energy able to escape that system over time, right? And that's why greenhouses warm up so significantly compared to the outside atmosphere, just because the glass and so on, that's lots of energy in, and the energy that tries to escape that system as infrared energy is less able to escape, right? Therefore, we're increasing the energy inside that system. That's why it warms up over time. Same thing happens in your car vehicle, right? Your car would not heat up nearly as much if you covered the glass of your windows, then less energy would be able to get in, and you wouldn't have that greenhouse impact in your car either, okay? But there are gases in our atmosphere, and we're really glad that they exist, right? That slow that rate of radiational cooling by absorbing some of that outgoing radiation, sending some of it back to the surface, okay? That's the greenhouse effect, super important to living systems because it keeps us from freezing, all right? But if we get an overabundance of these greenhouse gases, that's when we get the enhanced greenhouse effect and increased surface temperatures over time.